Hello, welcome back to Vedantu's NCERT Solutions for class 11 and 12. We are going to discuss the very first question from D and F block elements. So NCERT question 4.1. Write down the electronic configuration of these elements. So we need to write for chromium 3+, and we have promethium 3+, and we have copper plus, and cesium 4+, cobalt 2+, and we have lutetium 2+, and manganese 2+, and thorium 4+. So in here, we are going to discuss the electronic configuration. Basically, what is electronic configuration? It's nothing but it's the symbolic representation or notation of the manner in which the electrons are arranged in the or distributed in the different orbitals. So we are going to write for one by one. So for chromium, the atomic number is 24 and the electronic configuration of chromium is argon 3d5 4s1. So what is the electronic configuration of argon? It is 1s2 2s2 2p6 3s2 3p6 3d5 and 4s1. It is 3d5 and 4s1. So if we remove three electrons from chromium atom, it's going to be argon 3d3. This is the electronic configuration. So 1s2 2s2 2p6 3s2 3p6 3d3. This is the electronic configuration of chromium 3+. Chromium 3+. So let's move forward to the second one. Second one is promethium. So Pm3+. This is the element that has been given, the ion. So atomic number of promethium is 61. So the electronic configuration, xenon 4f5 6s2. So Pm3+, the electronic configuration is going to be xenon electronic configuration followed by 4f4, and it is going to be, yes, as there are 3 electrons that are removed, it is going to be 4f4. So let me write the configuration of xenon, and yes, 1s2 2s2 2p6 3s2 3p6 3d10. We have 4s2 then, and then we have 4p6 4d10. We have 5s2 5p6. This is the electronic configuration of xenon, and then we have promethium, so it is 4f4. This is the electronic configuration of promethium 3+ ion. And while we are writing the electronic configuration, we need to follow this rule, the diagonal rule. Alright, next one is, the third one is copper plus ion. So atomic number of copper is 29. So the electronic configuration of copper will be argon configuration followed by 3d10 4s1. As we are going to remove one electron, Cu plus ion, so one electron is removed, so it is going to be argon 3d10. 1s2 2s2 2p6 3s2. We have 3p6 and 3d10. This is the configuration of Cu plus ion. Next, we have cesium 4+ ion. Cesium 4+. So it is Ce 4+. Atomic number of cesium is 55. Atomic number of cesium is 55. So xenon, cesium, xenon followed by, we have, so cesium has the atomic number 55 and the electronic configuration will be, so yes, 54, xenon 54. So cesium can lose only one electron, okay, and it will become stable. So the electronic configuration will be 1s2 2s2 2p6 3s2 3p6 4s2 3d10, and we have 4p6 we have 5s2, 4d10 and 5p6. So this is going to be the electronic configuration. Moving on with the fifth one. So which is the fifth one? It is cobalt 2 plus. It is cobalt 2 plus. So the atomic number of cobalt is 27. So cobalt 2 plus, its electronic configuration is going to be argon 3d7. In detail, so 1s2, 2s2, 2p6, 3s2, 3p6, 3d7. So this is the electronic configuration of cobalt 2 plus. Alright, so how many number of electrons are there? Let's see. 2 plus 2, 4, 10, 12, 18, and then we have 18 plus 7. Okay, so there are 2 electrons that are being removed. So it's right. Next one. Sixth one. It is lutetium, Lu2 plus. It is lutetium. And the atomic number of lutetium is 71. Number of lutetium is 71. So the electronic configuration of lutetium 2 plus will be xenon, followed by, so 54 is the atomic number of xenon, followed by 4f14, 5d1. This is the electronic configuration. The lutetium electronic configuration, the elemental configuration is lutetium. So it is xenon 54, 4f14, 5d1 and 6s2. Okay, as we have removed these 2 electrons, it is 4f14, xenon followed by 4f14 and 5d1. Then we have the seventh one. Seventh one is, we have manganese 2 plus. This is a very simple one. Manganese, the atomic number of manganese is 25. Atomic number of manganese is equal to 25. So manganese electronic configuration, argon followed by 3d5, 4s2. So as we are removing 2 electrons, it is argon 3d5. That's it. Last one, eighth one is thorium, Th4 plus. It is thorium. The atomic number of thorium is 90. Atomic number of thorium is 90. So thorium 4 plus, its electronic configuration will be radon followed by 6d2, 7s2. So it is 62 and 7s2. So radon's atomic number is 86. Okay, so 86 plus 4, it's going to be 90. So it's the general electronic configuration. So thorium 4 plus, it is going to be radon, yes, 86. This is the electronic configuration. If we write in detail, so it is going to be 1s2, 2s2, 2p6, we have 3s2, 3p6, and we have 4s2, 3d10, 4p6, we have 4d10, and we have 4f14, and we have 5s2, 5p6, 5d10, 6s2, 6p6. This is the electronic configuration of thorium 4 plus ion. So we have discussed about a couple of ions as of now. So this number represents how many electrons are being removed. So if it is in negative charge, 3 minus or 2 minus, the electrons are being added. If it is in plus charge, so these metals are capable of losing electrons. They form cations. Upon losing electrons. So this is about the very first question, the electronic configuration of the respective ions. The question is, why are Mn2 plus compounds more stable than Fe2 plus towards oxidation to their plus 3 state? So we should know the electronic configuration of the respective ions that are given here. So if we look at it, The iron Fe has the electronic configuration argon 3d6 4s2, and manganese, it has the electronic configuration argon 3d5 and 4s2. So we know that if the orbitals are completely or half filled, then they are more stable. So the half and completely filled orbitals are very stable. Now look at the electronic configuration of Fe2 plus and Mn2 plus ions. So if we talk about Fe2 plus, then the electronic configuration will be argon 3d6, and Mn2 plus, it is going to be argon 3d5. So here this is half filled. Hence it is more stable. And if we write Fe3 plus, the electronic configuration of Fe3 plus ion, it is going to be argon 3d5. So what can we say? What can we deduce by this? So as half filled and completely filled orbitals are more stable, Mn, manganese, with +2 state has a stable that's half filled D5 configuration. So Mn2 plus shows resistance to oxidation to Mn3 plus, because Mn2 plus is already stable. So yes, but if we consider Fe2 plus has 3d6 configuration. On losing one electron, its configuration is going to be 3d5, which is half filled, and hence it is more stable. Okay, 3d5 configuration to be 3d5 configuration. Therefore, Fe2 plus is easily oxidized to 3 plus oxidation state. In order to solve these kind of questions, we need to know the electronic configuration of respective metal ions. Explain briefly how +2 state becomes more and more stable in the first half of the first row transition elements with increasing atomic number. So we are asked to explain how +2 oxidation state becomes more and more stable with respect to the first row transition elements. So first half of the first row transition elements, that's from scandium to we have manganese. First, let me write the oxidation state here. Element, I'll write the element and I'll write the electronic configuration of the respective element. Electronic configuration. I'm going to write the outer electronic configuration here. So argon is the nearest noble gas. So I'll write the oxidation states as well. Oxidation state. So when it comes to scandium, Sc, so 3d1 4s2. This is the outer electronic configuration of scandium. Oxidation state of scandium is +3 because it can exhibit +3 oxidation state. And if we talk about titanium 3d2 4s2. So plus 2, plus 3 and plus 4. These are the oxidation states that are exhibited by titanium. Then we have vanadium. So vanadium 3D3 4s2 plus 2 plus 3 plus 4 and plus 5. These are the oxidation states that are exhibited by vanadium. And then we have chromium 3D4 4s 3D5 4s1, because half-filled orbitals are stable, more stable. So 4s1 3D5, and it will exhibit plus 2 plus 3 plus 4 plus 5 and plus 6 oxidation states. And then we have manganese 3D5 4s2 3D5 4s2. So it is going to show plus 2 plus 3 plus 4 plus 5 and plus 6 as well as plus 7 oxidation state. Here chromium and manganese, they have half-filled orbitals, 3D orbitals, so they are more stable. And in the question they have asked us why plus 2 state becomes more and more stable in the first half of the first two transition elements. So what is the answer for this? It can be easily observed here. Except for scandium, all the other metals show plus 2 oxidation state here. Okay, so I'll write the answer. It can be observed that except scandium, all the other metals show plus 2 oxidation state. On moving from scandium to manganese. The atomic number increases. From 21 to 25. Scandium has atomic number 21 and manganese has atomic number 25. So which means that this means that the number of electrons in the 3D orbital increases from 1 to 5. Alright. So, scandium 2 plus. The electronic configuration is going to be 3D1. See here, 3D1. 2 electrons are removed from 4s. Alright. So, next we have titanium. Titanium plus 2. Oxidation state. So, it is going to be 3D2. Then we have vanadium 2 plus. So 3D3. And we have chromium 2 plus. 3D. What is the electronic configuration here? Chromium. So we are going to remove 2 electrons. So it is going to be 3D4. Then we have manganese plus 2. So 3D5. So this is half filled. Alright. So plus 2 oxidation state is attained by the loss of 4s electrons by all of these metals. So since the number of electrons since the number of electrons in d orbital, that is 3d orbital, increases from titanium 2 plus to manganese 2 plus, the stability of 2 plus oxidation state, plus 2 oxidation state increases. State increases. Because as the d orbital is getting filled. As the d orbital is getting filled. Okay. So yes, oxidation state increases. Manganese 2 plus has 3d5 electrons, which is half filled, hence it is highly stable, So as the plus 2 oxidation state happens in case of these metals, they are reaching the half filled electronic configuration. That's the reason the stability increases from scandium to manganese in their plus 2 oxidation state. The question is, to what extent do the electronic configurations decide the stability of oxidation states in the first series of the transition elements? Illustrate your answers with example. First and foremost, we need to remember this half filled and completely filled orbitals. Filled orbitals are very stable. When it comes to the first series of transition elements, they have 3D orbital. Okay, if it's 3D5 and 3D10, the respective metal is going to be extremely stable. The metal ion is going to be extremely stable. So which are the elements, which are the metals that are in first series? So we have scandium, we have titanium, and then we have vanadium, chromium, we have manganese, we have iron, cobalt, nickel, copper, and then we have zinc. Okay, so I'll write the electronic configuration here. So argon followed by 3d1, 4s2. Here for titanium 3d2. So of course argon is there, 3d2, 4s2. And then we have vanadium 3d3 and 4s2. Chromium 3d4, 4s1. Okay, so chromium is going to be half filled because it is more stable, 3d5 and 4s1. And then we have manganese where 3d5 and 4s2 is the electronic configuration. And which are the oxidation states that are exhibited by these respective elements? Let's see that. So this is about the first half of the elements. Okay, so let me write for iron as well. 3d6, 4s2, cobalt 3d7, 4s2, and nickel we have 3d8, 4s2, and then we have copper. So 3d10, 4s1. And for finally, we have zinc. So which has electronic configuration, I'll write it here. Zinc 3d10, 4s2. It's highly stable because it has completely filled orbital. So moving on with the oxidation state. Scandium shows +3 oxidation because if it loses all the 3 electrons, 2 from 4s and 1 from 3d, it is going to attain the nearest noble gas configuration, which is argon. So scandium is not going to show +2 oxidation state, rather it is going to show +3 oxidation state. Titanium is going to show +2 oxidation state, +3 oxidation state as well as +4. So vanadium +2, +3, +4 as well as +5. And chromium is going to show +2, +3, +4, +5 as well as +6 oxidation state. And manganese +2 to +7. And iron again +2 to +6. Cobalt +2 to +4. Okay, so the list goes on here. If you see the electronic configuration of all the metals here, what can we deduce? So the elements, we are considering the elements from the first half. Okay, the elements in the first half of the transition series. The transition series exhibit multiple oxidation states. Exhibit multiple oxidation states. states, and manganese, Mn, has maximum number of oxidation states. Maximum number of oxidation states. Oxidation states varying from +2 to +7. +2 to +7. And in the third question, we have discussed the stability of +2 oxidation state increases. So let's take the example of the same. The stability of +2 oxidation states, +2 oxidation state increases with increase in the atomic number, increase in atomic number. So scandium's atomic number is 21. Okay. So why does this happen? This happens as more electrons are getting filled in the d orbital. Scandium does not show +2 oxidation state. OS means oxidation state. So it shows +2 oxidation. It does not show +2 oxidation state, but +3, because its electronic configuration is 3d1 4s2. It loses all these electrons. It loses all the electrons to attain the configuration of argon, which is a noble gas. Configuration of argon. Okay. So +3 oxidation state of scandium is extremely stable, is highly stable. And if we look at manganese, for manganese, +2 oxidation state is very stable, because why? Let's see here, +2 oxidation state manganese. So it is going to be half filled. So if we remove these 2 electrons from 4s orbital, it is going to be half filled. Okay. So it is stable because 3d is half filled. Titanium +4 and vanadium +5. Vanadium +5 are also very stable for the same reason. If we see the electronic configuration, let me go back. So titanium +4 and vanadium +5. See here, titanium +4. It is going to be attaining the argon configuration, and vanadium +5, it is going to be attaining the argon configuration. Okay, noble gas configuration means it's very, very stable. Okay, so what happens here? So for manganese 2+, it is very stable. +2 oxidation state is very stable because after losing 2 electrons from 4s, manganese is attaining half-filled electronic configuration. 3d5. So this is one of the examples. So what can we say? the electronic configuration decide the stability of oxidation states in the first series of the transition elements. We have taken the examples of scandium, we have taken the example of manganese as well. What may be the stable oxidation state of the transition element with the following d electron configuration? They have given us the d electronic configuration. We should understand that it will have s electrons as well. 4s will be there. So in the ground state of their atoms, 3d3, 3d5, 3d8 and 3d4. So let's see the electronic configuration first. They have given us 3d electronic configuration in the ground state, not in their oxidation states. Okay, so if we talk about 3d, which is that first one, 3d3. So vanadium, right? It is vanadium's ground state configuration. So it is 3d3 4s2. 3d3 4s2. This is the actual electronic configuration. We have argon as well. Argon followed by 3d3 and 4s2. So what is the stable electronic configuration here? It can show +2 oxidation state if you remove 2 electrons from s orbital, and it can show +4 oxidation state. It can show +5 oxidation state as well. Okay, so it can show +3 oxidation state as well. And then we have 3d5. So 3d5, so whose electronic configuration is it? 3d5. So it can be chromium. Okay, it is chromium. So it has 3d5 4s1. Argon 3d5 4s1. So what will be the stable electronic configuration in case of chromium? So it's going to be +2. It is going to show +3 oxidation state, +4, +5 as well as +6. So +6 when we remove all the electrons from 4s and 3d orbital. 3d5 is not only shown by chromium, but manganese also shows 3d5 electronic configuration. Manganese. Argon 3d5 4s2. 3d5 4s2. So manganese shows oxidation states from +2 to +7. +2 to +7. And then we have the configuration 3d8. 3d8. So 3d8 is shown by nickel. It is shown by nickel. Okay. So yes, it is shown by nickel, and the electronic configuration is 3d8 4s2. 3d8 4s2. So the electronic configurations, oxidation states that are shown are +2 and +3 as well as +4. So +2 and +3 and +4. These are the oxidation states that are shown by nickel. And then we have 3d4 ground state configuration. Actually, 3d4 is not shown by any of the metals, because when it comes to chromium, it shows 3d5 4s1 configuration. Okay, why? Because 3d5, it is half filled. It is half filled. Rather than showing 3d4 and 4s2, it shows 3d5 4s1 electronic configuration, because half filled and completely filled orbitals are more stable. So 3d4, there is no 3d4 configuration. 3d4 configuration in the ground state. 3d4 is not shown by any of the transition 3d4 is not shown by any of the transition metals. This oxidation state is not shown. So when it comes to 3d8, so along with nickel, so 3d8 is shown by cobalt as well. Let me move on here. 3d8 is shown by cobalt as well. So what is the electronic configuration here? It shows 3d8 4s1. It shows 3d8 4s1. So it shows the stable oxidation states of +2 as well as +3. Okay. So yes, the stable oxidation states of transition element with a d electronic configuration 3d3, 3d5, 3d8 and 3d4. 3d4 is not shown by any of the metals, because 3d5 is more stable. Rather, being 3d4 4s2, chromium is going to attain Chromium is going to attain 3d5 4s1 electronic configuration because 3d5 is half filled here. Half filled and completely filled orbitals are extremely stable. Name the oxometal anions of the first series of the transition metals in which the metal exhibits the oxidation state equal to its group number. Anions are negatively charged ions. Anions are negatively charged ions. Negatively charged ions, while cations are positively charged. Cations are positively charged. Positively charged. So, which are the metals that belong to the first series of the transition metals? It starts from scandium. Okay, so it starts from scandium. There is vanadium, chromium, and we have manganese, cobalt, etc. So, in order to name the oxometal anions, we need to consider the oxidation state as well as the group number. They should be equal. Okay, so let's see one by one. First one is titanium. Titanium oxide. What is the formula here? TiO3 2 minus. If we calculate the oxidation state of titanium here, so we already know the group number. Let's see. Group number is 4. So oxidation state should also be 4. Let's see that. So yes, oxidation state is equal to X plus 3 into minus 2. Minus 2, the valency of oxygen. So oxidation state is minus 2 here. Here it is there. So X minus 6. So X is equal to plus 4. So both oxidation state and group number are 4. Next one, we have vanadate. Vanadate is also a transition metal. So VO3 minus. So group number to which vanadium belongs is 5. Group number is 5. Let's see the oxidation state here. Oxidation state is equal to, so X plus 3 into minus 2. 1 minus 1 is equal to X minus 6. X will be equal to 5. Okay. So group number and oxidation state are equal even in here. Vanadate. Next we have chromate. Chromate. The group number of chromium, group number to which chromium metal belongs is 6. Let's see the oxidation state. Oxidation state. I haven't written the formula. Okay. It is CrO4 2 minus. So X plus 4 into minus 2. Minus 2 is equal to X minus 8. X is equal to 6. So both group number and oxidation states are equal here. So if you see dichromate, we already know the group number. Okay. So dichromate Cr2O7, it is 2 minus. So oxidation state minus 2 is equal to 2x plus 7 into minus 2. So what will be the value? Minus 2 is equal to 2x minus 14. 2x minus 14. So 2x is equal to plus 14 minus 2. X is equal to 12 by 2. X is equal to 6. Even in chromate and dichromate, the oxidation state of chromium is plus 6. And the group number to which chromium belongs is also 6. And then we have permanganate. Permanganate. It is MnO4 minus. Oxidation state, let's see the group number to which manganese belongs is 7. Oxidation state, let's calculate. Oxidation state. So X plus 4 into minus 2. Minus 1. X minus 8. X is equal to 7. Both group number as well as oxidation state are equal here. What is lanthanoid contraction? What are the consequences of lanthanoid contraction? First, let's learn about what is lanthanoid contraction. Let me start with a new page here. So on moving along, the lanthanoid series. On moving along the lanthanoid series, atomic number increases. atomic number increases, and it increases by 1. Increases by 1. So as the atomic number increases, the number of protons and electrons, as well as and electrons also increases by 1. And the effective nuclear charge, increases as electrons are being added to the same shell. So what is this effective nuclear charge? Effective nuclear charge is nothing but net charge that is pulling electron towards the nucleus. So effective nuclear charge is the positive net charge that is pulling electrons towards the nucleus. So here the effective nuclear charge increases. Okay. So effective nuclear charge increases because the nuclear attraction due to addition of proton overpowers the interelectronic repulsion. Due to addition of electrons. Alright. So moving forward, with the increase in the atomic number, the number of 4f orbital increases. The number of electrons the number of electrons in the 4f orbital increases. And 4f electrons have poor shielding effect. Why? Because the electron density is less for both D and F shells. That's why. So 4f electrons have poor shielding effect. So what happens? Hence the effective nuclear charge experienced by the outer electrons increases. It results in an uniform or steady decrease in the size of the lanthanoids. So with an increase in the atomic number. atomic number. As atomic number increases, so there exists a uniform or steady decrease in the size of the lanthanoids. Atomic number. This is nothing but, this is called lanthanoid contraction. This is called lanthanoid contraction. And the second part of the question asks us to do what? Asks us to write the consequences of the lanthanoid contraction. So what are the consequences of this? Consequences of lanthanoid contraction. So the first one is, there is similarity. There are similarities in the properties of second and third transition series. Second and third transition series. And so there is variation in the basic strength of lanthanide hydroxide. Basic strength of lanthanide hydroxides. And what is the trend here? So the basic strength decreases from, lanthanum hydroxide to lutetium hydroxide. Okay. And the third consequence is separation of lanthanoids. Separation of lanthanoids is possible due to this lanthanoid contraction. So these are the consequences of lanthanoid contraction. So what are the characteristics of the transition elements and why are they called transition elements? Which of the D block elements may not be regarded as the transition elements? First, let's answer for the first question. What are the characteristics of transition elements? Characteristics or properties? Characteristics of transition elements. So transition elements generally have a high melting and boiling point. They have high melting and boiling points. And they are hard. And generally they have high density. They're hard and they have high density. And so they form paramagnetic compounds. Where electrons will be unpaired, paramagnetic compounds. And they form colored compounds. Because of paramagnetic nature, they form colored compounds. A transition occurs here, which is called DD transition. It's called DD transition. They form colored compounds. And yes, fifth one, they form stable compounds. They form stable complexes. And then they are pretty good conductors of electricity. So what are transition elements then? Transition elements are those elements. In which the atoms or ions contain partially filled d orbital. filled d orbital. These elements as in transition elements, lie in the d block and they show transition of properties. They show transition of properties between S block and P block. S block and P block. This is the reason why they are called transition elements. The name itself suggests. They show a transition of properties. They are called transition elements. Okay, but there are few elements. The elements such as zinc, mercury, and cadmium are they cannot be classified. They cannot be classified as transition elements because they have completely filled D. They have completely filled as in D10. Completely filled D subshell. Let's take the example of mercury here. So mercury, Hg. What is the electronic configuration here? Xenon, followed by 4f14, 5d10 and 6s2. Here we can evidently see that the D subshell is completely filled. Not just that, zinc also. So if we consider zinc, argon followed by 3d, 10, 4s2. So here also D is completely filled. So these elements cannot be considered under transition elements because transition elements are supposed to contain partially filled D subshell. The question is, in what way is the electronic configuration of the transition elements different from that of the non-transition elements? So we know that the transition elements should contain partially filled D orbital. So the transition elements of metals, they have a partially filled d orbital. Hence, the electronic configuration, the general electronic configuration here, the electronic configuration of transition elements is n-1 D 1 to 10 ns 0 to 2. Okay, so this is partially filled. But the non-transition elements either have a fully filled d orbital, or no d orbital at all. Therefore, the electronic configuration for non-transition elements, configuration of non-transition elements is ns1 to 2 or ns2 np1 to 6. Alright, so this is about transition elements configuration and non-transition elements configuration. Transition elements always have partially filled d orbital, while non-transition elements either have fully filled d orbitals or no d orbital at all. What are the different oxidation states exhibited by the lanthanoids? So in the lanthanoid series, lanthanoid series, plus 3 oxidation states, is predominant. Predominant because of three stages of ionization enthalpy are comparatively low. 3 stages of ionization enthalpies are comparatively low. So these elements will assume trivalent ionic states. These elements acquire plus 3 oxidation state. Alright. So most of the lanthanoids assume plus 3 or trivalent ionic states. There are exceptions though. Okay. Example, cerium 4 plus. So it exists in 4F0 configuration. And we have europium. So it exists in 4F7 configuration. And we have ytterbium, YB2 plus. It exists in 2 plus oxidation state. And the configuration will be the noble gas followed by 4F14. So yes, these are exceptions. So what we can deduce is that plus 2 and plus 4 oxidation states can also be found in the lanthanoid elements. Generally, they show plus 3 oxidation state, but there are exceptions like cerium, europium, and ytterbium. We are going to discuss the 11th question from D and F block elements. So the question has 4 sub-questions. First one, transition metals and many of their compounds show paramagnetic behavior. Explain. And we need to give the reasons. Next, second sub-question is the enthalpies of atomization of the transition metals are high. Third question, the transition metals generally form colored compounds. Fourth one, transition metals and their many compounds act as good catalysts. We need to give the reasons for the following statements here. So let's discuss the very first one. So which is transition metals show paramagnetic behavior. So the paramagnetism arises due to the presence of unpaired electrons. So each electron has a magnetic moment, that is associated with its spin angular momentum, and orbital angular momentum. In the first transition series, the orbital momentum, the orbital angular momentum is satisfied, is quenched. Quenched is nothing but satisfied. So the resulting paramagnetism is only because of the unpaired electrons that are present. Because of the unpaired electrons. And we have the second question. So second is to explain the enthalpy of atomization of the transition metals. So why they are high. Okay. So second one. So transition elements have a highly effective nuclear charge. And also a large number of valence electrons. But what is this, enthalpy of atomization? So, enthalpy of atomization, it is nothing but, it's the mutation in the enthalpy, mutation as in change in the enthalpy that occurs when a molecule of a substance is reversed into existing atoms in a gaseous state. This is nothing but enthalpy of atomization. So, as we have already discussed, transition elements have a highly effective nuclear charge and they have a large number of valence electrons. Alright. Therefore, they form very strong metallic bonds. Because of high effective nuclear charge and a large number of valence electrons, they form a very strong metallic bonds. And as a result, the enthalpy of atomization of transition metals are high. And then the third one was the transition metals generally form colored compounds. So this will be this is studied in coordination compounds as well. So the third one, most of the complexes of transition metals are colored. Most of the complexes of transition metals are colored. This is because of DD transition. So, this is because of the absorption of, in one word, it is DD transition. Let me explain this. So, this is because of the absorption of radiation from the visible region. Radiation from the visible light region to promote an electron from one of the d orbitals to another. Transition occurs here. So electron donating species are called ligands. So in presence of ligands, the d orbitals. So we will be discussing in detail about ligands in coordination compounds. As of now, so ligands are the electron donating species. In presence of ligands, the d orbitals splits up into two sets of orbitals having different energies, T2g and dg, having different energies. Therefore, the transition of electrons from, so the transition of electrons can take place from one set to another. The energy that is required for these transitions, is quite small and falls in the visible region of the radiation. Thus, the ions of transition metals absorb the radiation of particular wavelength and the rest is reflected. Imparting the color to the solution. Different complexes exhibit different colors in the solution. Next, fourth statement was transition metals and their many compounds act as good catalysts. So catalysts are those substances which do not participate in the reaction, but they increase or decrease the rate of the reaction. Okay, so transition metals are very good conductors because the catalytic activity of transition metals can be explained by 2 points. Okay, so first one, transition metals provide suitable surface. They provide suitable surface for the reactions to occur. As I already mentioned, they do not take part in the reaction. They only accelerate or decelerates the rate of the reaction. So they provide suitable surface for the reaction to occur. And then the second point is, so they have the ability to show different oxidation states. They have the ability to show different oxidation states. And form complexes. So these metals form unstable intermediate compounds. They form unstable intermediate complexes. Let me rub this off. They form unstable intermediate complexes. They form unstable intermediate complexes or compounds. So they provide a new path with lower activation energy with lower activation energy. Activation energy for the reaction to happen. For the reaction to occur. So lower the activation energy, better will be the reaction. Okay, faster will be the reaction. So we have explained the reasons for all the 4 statements. So first one was transition metals and many of their compounds show paramagnetic behavior. It's because of the unpaired electrons, and the enthalpies of atomization of the transition metals are high. And then transition metals generally form colored compounds. That's because of DD transition. And the last one was transition metals and their many compounds are good catalysts because they provide surface and they form unstable intermediate complexes. So which provide a new path to the new path with lower activation energy. What are interstitial compounds? Why are such compounds well known for transition metals? So first, what are interstitial compounds? Let's see that. Interstitial compounds. Interstitial compounds. So these are the compounds that are formed. The compounds formed when small atoms such as hydrogen, carbon or nitrogen gets trapped inside the crystal lattice. Inside the crystal lattice of metals are known as interstitial compounds. Interstitial compounds. So why are such compounds, interstitial compounds, are well known for transition metals? So transition metals are large in size. Transition metals are large in size and they contain a lot of interstitial sites. They contain a lot of interstitial sites. So these sites can be used to trap atoms of other elements. Which have small atomic sizes. So yes, transition elements are well known for these interstitial compounds because they are large in size and they contain lot of interstitial sites where the compounds, where the small atoms such as hydrogen, carbon or nitrogen can be trapped inside the crystal lattice. How is the variability in oxidation states of transition metals different from that of the non-transition metals? Illustrate with examples. So transition metals, so they have the transition properties from S to P block. So in transition elements, the oxidation states vary by unity 1. Okay, so example can be given manganese. Manganese exhibits +2, +3, +4, +5, +6 and +7 oxidation states, all differing by 1. But if we consider non-transition elements, in non-transition elements, the variation is selective. It differs by not one but two. Example, so sulfur exhibits 2, 4 and 6 oxidation states, differing by 2 oxidation states. And we have nitrogen, which is a non-transition element. Nitrogen exhibits 3 and 5 oxidation states. 5 oxidation states. But in here, sulfur and nitrogen are not metals. These are non-metals. If we consider non-transition metals, so we can take the example of tin. Tin shows +2 and +4 oxidation states. And we have indium. Indium shows +1 and +3 oxidation states, differing by 2. But in transition elements, so the oxidation states vary by 1 unit. Okay. So this is about variability in oxidation states of transition metals and non-transition metals. They are different. Describe the preparation of potassium dichromate from iron chromite ore. What is the effect of increasing pH on a solution of potassium dichromate? So we have the iron dichromate ore. So we need to, iron chromate ore, sorry. So we need to convert that into potassium dichromate. How are we going to do that? First step, we have 3 steps. First step is to preparation of sodium chromate. Preparation of sodium chromate. Here, what are we going to make? What are we going to do? So we are going to make this iron chromite ore to react with sodium hydroxide, that's caustic soda, and oxygen, and it will be converted into sodium chromate. Along with that, Fe2O3 and water are the products. Step 2. What are we going to do? We have sodium chromate now. So we are going to convert the sodium chromate, conversion of sodium chromate into sodium dichromate. So what is the reaction here? We have sodium chromate as of now, Na2CrO4, 2Na2CrO4 plus concentrated H2SO4. It is made to react with sulfuric acid. It leads to the formation of Na2Cr2O7, potassium dichromate. Along with that, we'll get Na2SO4, sodium sulfate and water. Now step 3. We have sodium dichromate now. So conversion of sodium dichromate into potassium dichromate. Conversion of sodium dichromate into potassium dichromate. So the reaction is as follows: Na2Cr2O7 plus 2KCl, potassium chloride. We are going to react sodium dichromate with potassium chloride. It leads to the formation of K2Cr2O7, which is potassium dichromate. Along with that, we'll get 2NaCl, sodium chloride. But here, potassium chloride is less soluble. Is less soluble than sodium chloride, NaCl. And is obtained in the form of orange colored crystals. So this is this is not potassium chloride, but this is potassium dichromate. These are the products, right? We have potassium dichromate as well as sodium chloride. So potassium dichromate is less soluble than sodium chloride and it is obtained in the form of orange colored crystals. It can be removed by filtration method. And they have asked another question: what is the effect of pH? Effect of increasing pH on a solution of potassium dichromate. So this is something we need to keep in mind. The dichromate ion, that is Cr2O7 2 minus, and chromate ion that is CrO4 2 minus are in equilibrium at pH 4. So pH 4 indicates acidic pH. Below 7, so it indicates acidic pH. Above 7, it indicates basic pH. So 2 CrO4 2 minus when the medium is acidic. So it will become 2HCrO4 minus. Okay, and it becomes Cr2O7 2 minus. So this is yellow in color. This is dichromate, and this is this is orange in color, dichromate, and this is yellow in color. And the same applies for dichromate, Cr2O7 2 minus. So in base, so it gives HCrO4 minus. Okay, and it gives chromate ion, 2CrO4 2 minus ion. So what happens here? By changing the pH, they as in chromate and dichromate can be interconverted. Describe the oxidizing action of potassium dichromate and write the ionic equations for its reaction with iron solution. So this is, yes, iron solution. Let me correct it. It is iron solution and H2S, hydrogen sulfide. So potassium dichromate, K2Cr2O7, is a very good oxidizing agent. Is a very strong oxidizing agent. So what is an oxidizing agent? So oxidizing agent or oxidant. So yes, oxidant is a substance which oxidizes the other, itself undergoing reduction. So what is reduction? It is addition of electrons. Reduction is addition of electrons. And oxidation is removal of electrons. So if we see the first one, that is iodine. So K2Cr2O7 oxidizes iodine in acidic medium. So it's a very good oxidizing agent, potassium dichromate, but it acts in acidic medium. Okay. So what's going to happen? K2Cr2, let me rub this off. Oxidizes in acidic medium. It's a good oxidizing agent. K2Cr2O7 plus 4H2SO4 gives K2SO4, potassium sulfate, and chromium sulfate, K2SO4 thrice, 4H2O, and 3 oxygen, nascent oxygen. Okay, so this is the reaction. First one, we have iodine. So 2Cr2O7 2 minus plus 14H plus 6 electron gives 2Cr3 plus and 7H2O. You can see the change in oxidation state here. Let me show you. So Cr2O7, right? 2x plus 7 into minus 2. That's the valency of oxygen is equal to minus 2. So 2x minus 14 is equal to minus 2. 2x is equal to 12. So X is equal to plus 6. So here plus 6 oxidation state 2, it has become plus 3. Okay. So the oxidation state has been changed. So addition of electron is happening here. Okay. All right. So next step as in next equation. So 2i minus 2 I2, it is getting reduced, oxidized, sorry, into 3. So what will be happening here? 2Cr2O7 2 minus plus 6i minus plus 14H plus gives 2Cr3 plus chromium 3 plus ion and 3i2, and then we have 7H2O. Okay. So iodine has been oxidized now. This is the equation. Next, we have the second one. Second one where we have to oxidize iron. Okay. So K2Cr2O7 oxidizes oxidizes Fe2, that is ferrous ion to oxidizes Fe2 to Fe3, that is ferrous ions to ferric ions. Here is the equation. 2Cr2O7 2 minus plus 14H plus 6 electrons gives 2Cr3 plus 7H2O. Okay. So we have Fe2 plus now. So it will be oxidized to Fe3 plus. Oxidation means removal of electron. Fe2 plus to Fe3 plus electron. This will be multiplied by 6. Okay. 2Cr2O7 2 minus plus 14H plus 6 electrons, that is Fe2 plus 6 Fe2 plus gives 2Cr3 plus 6 Fe3 plus and 7H2O here. So there are 6 Fe3 plus ions and 6 Fe2 plus ions, and we have 14 H plus ions. So this is the equation. Moving on, we had H2S2 oxidize. So K2Cr2O7 oxidizes H2S2S. So oxidation is nothing but removal of hydrogen as well. Addition of oxygen or removal of hydrogen. So what will happen here? The same equation. 2Cr2O7 plus 2 minus plus 14H plus 6 electron gives 2Cr3 plus 7H2O. Okay. So H2S is being oxidized to S. S plus 2H plus 2 electrons. This will be multiplied by 3. Let's balance it. 2Cr2O7 2 minus. So we have 14H plus. Here we have 6H plus. So if you minus this, it will be 8H plus 3H2S, because we have multiplied H2S by 3, giving 2Cr3 plus 3 sulfur 7H2O. So this is the equation. So potassium dichromate is a very strong oxidizing agent. So describe the preparation of potassium permanganate. How does the acidified permanganate solution react with iron 2 ions, SO2, sulfur dioxide, and oxalic acid? We need to write the ionic equations for these reactions. Okay, we need to write the ionic equations. So let's get started. First step. So first, question is to describe the preparation of potassium permanganate. How potassium permanganate is prepared. So potassium permanganate, KMnO4. It is produced from, prepared. It is prepared from pyrolusite ore. That is MnO2. MnO2, manganese dioxide. So first step is to, this pyrolusite ore is fused or made to react with potassium hydroxide, KOH, or K2CO3, potassium carbonate, in presence of air, that is oxygen. Okay, or any oxidizing agent, oxidizing agent such as KNO3, potassium nitrate, or KClO3. So what is it going to give? So pyrolusite is fused with KOH to give potassium manganate, potassium manganate. So potassium manganate is K2MnO2. This is a green colored mass. It is a green colored mass. So the reaction is as follows. 2MnO2, that is pyrolusite, is fused with KOH to, along with oxygen, to produce 2K2MnO4. This is the green mass along with water. So next step is to extraction of potassium manganate, extraction of K2MnO4 with water, followed by the oxidation with chlorine. Chlorine is a very good oxidizing agent. Or we can use ozone, O3, or carbon dioxide as well. Okay? Potassium permanganate. Simple. So just in 2 steps we are going to obtain potassium permanganate. So what are we going to do? K2MnO4 plus Cl2 gives KCl and 2KMnO4. We need to balance the equation. So 2K2MnO4 plus Cl2 gives 2KCl plus 2KMnO4. We have gotten potassium permanganate. So on concentrating this solution, so dark purple colored crystals of potassium permanganate is separated out. It is separated out. Okay. So yeah, moving forward. So reactions of acidified KMnO4 solution with we have iron first, iron 2 ion. Okay, it is as follows. 2MnO4 minus, this is not 2 minus, this is just minus MnO4 minus plus 10 Fe2 plus 16H plus gives 2Mn2 plus 10 Fe3 plus 8H2O. Then we have first one iron 2 ion. Second one we have with sulfur dioxide. So the reaction is as follows. 2MnO4 minus plus 5SO2 plus 2H2 gives 5SO4 2 minus sulfate ion, and then we have 2Mn2 plus and 4H plus. Okay, so there is a note. So we'll discuss for oxalic acid and then we'll discuss that oxalic acid. So 2MnO4 minus plus 5C2O4 2 minus oxalate ion. So 16H plus gives 2Mn2 plus 8H2O plus 10CO2. This is the reaction. So they have asked us to write the ionic equation. So this is the equation. So there is a note. In neutral or acidic medium, manganate ion will disproportionate. It will disproportionate to permanganate ion. Okay. 3MnO4 2 minus plus 4H plus gives 2MnO4 minus. So this is permanganate plus MnO2 manganese dioxide plus 2H2O. Okay. So yes. So in neutral or acidic medium, they have asked us what? So how does acidified permanganate solution react with iron 2 ions, SO2 and oxalic acid? That is the reason. So they have specifically mentioned acidic. Okay, that's why we have taken this 2MnO4 minus everywhere. Okay, so yes, this is the answer. So we have discussed the preparation of potassium permanganate from pyrrolosite ore, and we have discussed how acidified permanganate solution react with different substances here. For M2 plus M and M3 plus M2 plus systems, the standard electrode potential values are given here. Okay, using this data, we have to comment on the stability of Fe3 plus in acid solutions as compared to that of chromium 3 plus and manganese 3 plus, and also the ease with which iron can be oxidized as compared to a similar process for either chromium or manganese metal. So I have given you the data here properly. Okay, so what's happening here? As you can see, the high value for manganese, it is so Mn3 plus 2, Mn2 plus, it is plus 1.5 volt. So what's going to happen? Let me change the color. So high value of manganese shows that Mn2 plus, that is D5 system, okay, is stable. What is the value? It is plus 1.5 volt. So comparatively, so iron Fe3 plus to Fe2 plus, the standard electrode potential is quite less compared to plus 1.5, it is plus 1.8. So comparatively, the low value for Fe shows extra stability of Fe3 plus. So Fe3 plus also is in D5 system, half filled. Okay. So what is the value? It is plus 0.8 volt. Plus 0.8 volt. Next we have chromium here. It is minus 0.4 volt. So chromium 3 plus is very, very stable. Is very, very stable and cannot be reduced. To chromium 2 plus. So what will be the order here? So Fe3 plus is more stable than Mn3 plus, but less stable than chromium 3 plus. Okay, because chromium 3 plus to 2 plus, so it has negative electrode potential value. Then we have the next sub question. So manganese 2 plus to manganese plus 1, so has negative most negative reduction potential or electrode potential. Reduction potential. You can see there, right? And it is most easily oxidized. So it has the most negative reduction potential. That's why it can be easily oxidized. So the ease of the oxidation will be the ease of oxidation is. So manganese, then chromium, and then we have iron. So manganese, chromium, and iron. See here, we can see the values. Let me change the color here. See. So manganese. Then we have chromium and then iron. Okay. Yes. Manganese, chromium, and then iron. Predict which of the following will be colored in aqueous solution. So we are given with couple of ions here. So we have to give reasons for each. First, let's see. So which are all the ions are there. First of all, when the complexes are colored, when there is incomplete d orbital. When there is incomplete d orbital, so the dd transition occurs. The dd transition is possible. It is possible. So the compounds are colored. The compounds are colored. And when there is empty or fully filled d orbital, dd transition do not occur. So dd transition is not possible. It is not possible. So the complex will be colorless. It will be colorless. If we look at the ions that are given here, we need to first write the element, its atomic number. So ionic state is given here, ionic state, and we need to write the electronic configuration. For which in ionic state. First one is titanium. So atomic number is 22. The ionic state is Ti3 plus. Okay, 3 plus ionic state. So argon 3D1. Next we have vanadium. 23 is atomic number. So V3 plus. This is the ion given. So argon 3D2. Next we have copper. So 29 Cu plus is given. Argon 3D10. Next we have scandium. 21 is atomic number of scandium. Ionic state that's given in the question is Sc3 plus, 3 plus ionic state. Argon 3D0. Next we have manganese. So atomic number is 25. So the state is Mn2 plus. It is Mn2 plus. And argon 3D5. Let me move to the next page here. 3D5. And then we have iron. Atomic number is 26. Fe3 plus is given. And the configuration is argon followed by 3D5. Next we have cobalt. It is 27. Cobalt 2 plus. So argon followed by 3D7. If we take a look at this, so which are incompletely filled? That is Fe3 plus incompletely filled, cobalt 2 plus incompletely filled, and we have titanium 3 plus incompletely filled, vanadium 3 plus, yes, incompletely filled, and copper plus, it is completely filled. The d orbital is completely filled. So is scandium. It is colorless because here also, so scandium 3 plus, here the d orbital is empty. So what can we deduce here? As scandium 3 plus ion does not contain any electrons in its d orbital, as it is empty. D orbital is empty. And then what else do we have? We have Cu plus. It is completely filled. And Cu plus is has completely filled d orbital. Completely filled d orbital. Thus, these two ions will be colorless in aqueous solution. Okay, the question is, so yeah, will be colored, they have asked. So apart from these, except these, so yeah, titanium 3 plus, we have vanadium 3 plus, and Mn2 plus, Fe3 plus, cobalt 2 plus. All of these ions are all of these will be colored in aqueous solution as they have incomplete d orbital. Compare the stability of +2 oxidation state for the elements of the first transition series. So in the first transition series, so what are all the elements that we have? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Right? So this is the table where so the oxidation states of different elements can be seen here. So if we look at this table from scandium to manganese, the number of oxidation states are increased, right? So manganese is showing the maximum number of oxidation states. So it is varying from +1 to +7. Okay, so let's write the answer. So from the above table, we can see that manganese shows the maximum number of, oxidation states changing from +1 to +7. Okay, so the number of oxidation states increases as we move from scandium to manganese. And then again, so manganese to zinc, the number of oxidation states decreases. So on moving from manganese to zinc, the number of oxidation states decreases due to a decrease in the, why does the number of oxidation state decreases here? Because there is a decreased in the number of available unpaired electrons. If we talk about the relative stability, so of +2 oxidation state, the relative stability of +2 oxidation state increases on moving from top to bottom. That is from scandium to what do we have? Zinc. Okay, so it increases from the stability of +2 oxidation state increases on moving from top to bottom, because on moving to the bottom from the top, it becomes more and more difficult, more and more difficult to remove the third electron, the third electron from the d orbital, from the d orbital. Thus, the stability of +2 oxidation state increases on moving from top to bottom. Okay, so on moving to the moving to the bottom from the top, it becomes very very difficult for us to remove the third electron from the d orbital. Compare the chemistry of actinoids with that of the lanthanoids with special reference to electronic configuration. We need to compare the actinoids and lanthanoids with respect to their electronic configuration, atomic sizes and ionic sizes, oxidation state, and chemical reactivity. So let's get started. First one is, okay, let me change the color. So electronic configuration. Electronic configuration. This is pretty simple. So when we talk about the electronic configuration, the general electronic configuration of the general electronic EC, I'm going to write EC, electronic configuration of lanthanides. Lanthanides is xenon followed by 4F 0 to 14, 5D 0 to 10, 0 to 10, and 6S 2. Okay, and the general configuration and general electronic configuration of actinoids is radon followed by 5F1 to 14, 6D 0 to 10, and 7S2. Okay, so yeah, this is the electronic configuration. We have compared that. Moving on to the second factor that we need to discuss is atomic size and ionic sizes of lanthanoids and actinoids. Atomic and ionic sizes. Ionic sizes. So yeah, just like lanthanoids, actinoids also show actinoid contraction. Lanthanoids show lanthanoid contraction, actinoids show actinoid contraction. So what is actinoid contraction? It is the overall decrease in atomic and ionic radii. Atomic and ionic radii. So the contraction is greater due to the poor shielding effect of pi f orbitals. Okay, next the third factor is about oxidation state. So lanthanoids as well as actinoids show variable oxidation states. So yeah, the principal oxidation state OS of lanthanoids is +3. Okay, so sometimes we see the oxidation state of +2 as well as +4. See the oxidation state of +2 and +4 as well. Why? Because this is because of the extra stability of half filled and completely filled and completely filled orbitals. Okay. Just like lanthanoids, actinoids show a greater range of oxidation states because of the comparable 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 energies of the orbitals, the respective orbitals. Like there is 5f and 6d and 7s orbitals. 7s orbitals. Okay. So here also, even here, plus 3 is the principal oxidation state. Okay. So actinoids such as lanthanoids have more compounds in plus 3 state than the plus 4 than the plus 4 state. This is about the comparison of lanthanoids and actinoids with respect to their oxidation states. Next is to discuss about the chemical reactivity. Fourth one, chemical reactivity. Chemical reactivity. So in the lanthanoid series, the the earlier members are more reactive. So their reactivity can be compared to calcium. So how calcium reacts, that's how we can compare the lanthanoid, the earlier members of the lanthanoid series, how they're going to be reactive. Okay. So with an increase in atomic number, so these elements, lanthanoids, start behaving similar to that of aluminium. Okay. If we talk about actinoids, are highly reactive metals. So the reactivity increases when they are finely divided. And yeah, so actinoids are highly reactive metals, especially when they are finely divided. So when they are added to boiling water, they give a mixture of oxide and hydride. The respective oxides and hydrates are produced. So actinoids combine with most of the nonmetals at moderate temperature. At moderate temperature. If you talk about alkalis, alkalis do not have any action on actinoids. But yeah, so in case of acids, actinoids are slightly affected by nitric acid, HNO2, as there is formation, of a protective oxide layer, a protective oxide layer. All right. So we have discussed the comparison between actinides and lanthanoids with respect to their electronic configuration, atomic number, atomic and ionic size, oxidation state, as well as chemical reactivity. How would you account for the following? We have three sub questions here. Of the D4 species, chromium 2 plus is strongly reducing while manganese 3 is strongly oxidizing. Second one, cobalt 2 is stable in aqueous solution, but in the presence of complexing reagents, it is easily oxidized. Third one, the D1 configuration is very unstable in ions. So let's discuss the very first one. So they have mentioned that chromium 2 plus is strongly reducing, right? So what is the reason? So chromium 2 plus is strongly reducing in nature, strongly reducing in nature. Okay, so it has D4 configuration. It has D4 configuration. So while it is reducing the other, itself it undergoes oxidation. So reducing agent is something which itself undergoes oxidation, reducing the other. It undergoes oxidation and is oxidized to chromium 3 plus. Here D3 configuration will be there. Okay. So this D3 configuration is a more stable configuration. But on the other hand, we have another ion, which is that manganese. So Mn3 plus. So it is in D4 configuration, acts as oxidizing agent. It acts as an oxidizing agent, and it is reduced to Mn2 plus. That is D5 configuration. So this D5 configuration, this has a half-filled d orbital. So it is stable, which is highly stable. Okay. Moving on to the second question. In the second question, we had cobalt. Cobalt 2 is stable in an aqueous solution, but in presence of complexing reagents, so it is easily oxidized. So what is the reason? So cobalt 2, is it cobalt 2? Yes, it is cobalt 2. Cobalt 2 is stable in aqueous solutions. Aqua means water. Aqueous solutions. In presence of strong field ligands, it is oxidized to cobalt 3. Okay. So the third ionization energy of cobalt is high. So the higher amount of CFSE amount of CFSE, that is crystal field CFSE, stabilization energy. Crystal field stabilization energy is released in presence of strong field ligands. So this energy is going to overcome the ionization energy. So the third ionization energy of cobalt is high. The higher amount of CFSE is released in presence of strong field ligand, overcomes the ionization energy. Moving on to the third sub question. So third sub question says that, so the D1 configuration is very unstable in ions. So the ions in D1 configuration, tend to lose one electron to get into stable D0 configuration. The hydration energy is more than sufficient to remove this only one electron that is present. Remove the only electron present in d orbital. So they are going to act as reducing agents. The question is, what is meant by disproportionation? Give two examples of disproportionation reaction in aqueous solutions. So let's discuss that. So what is disproportionation reaction? First of all, what is going to happen? So here, a relatively less stable oxidation state, undergoes an oxidation reduction reaction, that is nothing but redox reaction, oxidation reduction reaction simultaneously is called, so a relatively less stable oxidation state undergoes an oxidation reduction reaction simultaneously. This, it is called disproportionation reaction. So we are asked to give two examples for this in aqueous solutions. So here is an example. The first example, chromium oxide is going to undergo disproportionation reaction. Okay, this is the reaction. You can actually find out the oxidation state here. Okay. So here what's happening? So chromium, which is in its fifth oxidation state, is oxidized to chromium 6. Okay, and it is reduced to chromium 3. See, evidently here you can check the oxidation state. Okay, so this chromium has undergone oxidation. Okay, it is oxidized to chromium 6 in here, and it is reduced to chromium 3 here, chromium 3 plus. Another example can be given here. So this is the reaction. Manganese oxide will be undergoing disproportionation reaction to give 2MnO4 minus plus MnO2 plus 2H2O. Here, so Mn is in its sixth oxidation state, 5-6 oxidation state, is oxidized to Mn7 and reduced to Mn 4. So here to here it is oxidized. It is oxidized. From here to here it is reduced. So simultaneously it is oxidized as well as reduced. That's why. So it is called a disproportionation reaction. Which metal in the first series of transition metals exhibits +1 oxidation state most frequently and why? So this has something to do with the complete, achieving the, stable configuration. So in the first series, this is very simple actually. So in the first series of transition metals, copper exhibits +1 oxidation state, very frequently. We know that copper's electronic configuration. Copper has an electronic configuration of argon, so followed by 3d10 and 4s1 configuration. So what is it going to do? It is going to lose its 1 electron from 4s orbital and it is going to attain completely filled d orbital. Okay, so it is going to lose one electron and attain the stable, that is completely filled d orbital. So hence it is very, very stable. Question number 24. Calculate the number of unpaired electrons in the following gaseous ions: Mn3+, chromium 3+, vanadium 3+, and titanium 3+. Which one of these is the most stable in aqueous solution? Let's get started. In order to solve this question, we need to know the electronic configuration of the respective transition metals. So if we consider manganese, the first one is manganese. Yes, Mn2+. So its electronic configuration will be argon 3d4. So the number of unpaired electrons is 4 here in this case. Second one, we have chromium 3+. So its electronic configuration is as follows: argon 3d3. So it has 3 unpaired electrons. And then we have vanadium. So vanadium, it is argon 3d2. So there are 2 unpaired electrons. And the fourth one is titanium 3+. The electronic configuration is argon followed by 3d1, and its the number of unpaired electron is 1. So here chromium 3+ is the most stable in aqueous solution. Because what is the reason? Because of its T2G3 configuration. That's all. So it's a very simple question. So chromium 3+ is the most stable amongst these 4 ions in aqueous solution. Question number 24. Calculate the number of unpaired electrons in the following gaseous ions: Mn3+, chromium 3+, vanadium 3+, and titanium 3+. Which one of these is the most stable in aqueous solution? Let's get started. In order to solve this question, we need to know the electronic configuration of the respective transition metals. So if we consider manganese, the first one is manganese. Yes, Mn2+. So its electronic configuration will be argon 3d4. So the number of unpaired electrons is 4 here in this case. Second one, we have chromium 3+. So its electronic configuration is as follows: argon 3d3. So it has 3 unpaired electrons. And then we have vanadium. So vanadium, it is argon 3d2. So there are 2 unpaired electrons, and the fourth one is titanium 3 plus. The electronic configuration is argon followed by 3d1, and its the number of unpaired electron is 1. So here chromium 3 plus is the most stable in aqueous solution, because what is the reason? Because of its T2G3 configuration. That's all. So it's a very simple question. So chromium 3 plus is the most stable amongst these 4 ions in aqueous solution. Question number 26. Indicate the steps in the preparation of K2Cr2O7 from chromite ore. Second one, KMnO4 from pyrolusite ore. We need to mention the reactions as well. First thing, we'll prepare K2Cr2O7 from chromite ore. How do we do that? So potassium dichromate. What is potassium dichromate? K2Cr2O7. Potassium dichromate is prepared from chromite ore. What is the formula? It is FeCr2O4. This is chromite ore. In the following steps. So first one, step 1. What is the first step? Preparation of sodium chromate. So this FeCr2O4, this is chromite ore. It is taken and it is made to react with sodium hydroxide in presence of oxygen. Okay, we always have to write the balanced chemical equation. This is going to result in the formation of sodium chromate, that is Na2CrO4 and Fe2O3 and H2O. Is it balanced? It's not balanced. Always make sure to write the balanced equation. Okay, so now we have gotten sodium chromate. Okay, now what is the second step? Step 2. What do we need to do? So sodium chromate is converted into sodium dichromate. We need to make sodium chromate react with H2SO4, concentrated H2SO4. So we'll take sodium chromate now, 2Ne2Cr O4, made to react with concentrated H2SO4, will result in the formation of sodium dichromate, Na2Cr2O3, and we'll get sodium sulfate as a product, one of the products, and water. Now step 3. What is step 3? So conversion of this sodium dichromate to potassium dichromate. How do we do that? We are going to make sodium dichromate react with potassium chloride. Okay, Na2Cr2O7, it is not O3, it is O7. Na2Cr2O7 is made to react with KCl, potassium chloride, to give K2Cr2O7 along with 2NaCl. But potassium chloride is less soluble than sodium chloride and is obtained in the form of orange colored crystals. colored crystals, and it can be separated. It can be separated by filtration technique. Filtration. Okay. And dichromate ion exists in equilibrium with chromate ion. But the pH condition needs to be maintained. At what pH? At pH is equal to 4. So what is pH 4? It is slightly acidic pH. Okay. So next one is to prepare potassium permanganate, okay, from pyrolusite. So preparation, this is the answer for the second sub question. Preparation of potassium permanganate, that is KMnO4, from pyrolusite. What is pyrolusite? It is nothing but manganese dioxide. Okay. The ore is fused. Which is the ore? The pyrolusite. The ore is fused with potassium hydroxide in presence of atmospheric oxygen. Or we can also use oxidizing agent. OE is oxidizing agents like KNO3, potassium nitrate, or KClO4, potassium chlorate, okay, to give KMnO4, that is potassium permanganate. Okay. So what is the reaction? 2MnO2 is made to react with KOH in presence of oxygen. It should be heated and it will give 2K2MnO4 plus 2H2O. Okay. And the green mass, K2MnO4 is the green mass, is extracted with water. It is extracted with water and oxidized by electrolysis or by passing chlorine or ozone into the solution. So chlorine and ozones are very good oxidizing agents. Okay. So if it is electrolytic oxidation, this is the reaction. K2MnO4, O4. This is the green mass. Yes. So electrolysis is happening. So ions will be formed here. 2K plus and MnO4, 2 minus ion. Okay. H plus and OH minus ion. And what will be produced at anode? At anode, manganate ions are oxidized. To permanganate ions. Okay. MnO4, 2 minus. It will be oxidized to MnO4 minus, and 1 electron will be removed. So if it is by chlorine, if chlorine is used as an oxidizing agent, oxidation by chlorine, what is the reaction that is involved here? 2K2MnO4 plus Cl2 gives 2KMnO4 plus 2KCl. Okay. 2MnO4 2 minus plus chlorine. Yes. 2MnO4 minus plus 2Cl minus. Okay. So this is permanganate ion. Okay, this is permanganate ion. So this is manganate ion. This will be oxidized to permanganate ion. Okay. So if it is oxidation by ozone, oxidation using ozone. What is ozone? It is O3. Okay. 2K2 MnO4 plus O3 plus H2O. It gives 2KMnO4 plus 2KOH plus O2. Okay. So 2MnO4 2 minus plus O2 gives 2MnO4 2 minus plus 2OH minus plus O2. So if they ask you to, ask you to explain how this permanganate is produced from pyrolusite ore, you can either make use of electrolytic oxidation or by using oxidizing agent chlorine or ozone. Okay, so you can choose to write either one of these. You don't have to write all of these. So you can choose to write either one of these, whichever suits best for you, whichever is easy for you. Question number 27. What are alloys? Name an important alloy which contains some of the lanthanoid metals and mention its uses. So what are alloys? Alloys are something that we have studied in grade 9 as well. Alloys. So the homogeneous mixture of two or more elements in which at least one will be a metal. In which at least one will be a metal. Example: brass, bronze, stainless steel. These are examples for alloys. But they have asked us to specifically mention about an alloy which has lanthanoid metals. So an important alloy of lanthanoids is mesh metal. What does it contain? We'll move on to the next page. It contains lanthanoids. About 94 to 95% of lanthanoids is present in this, and iron is present in 5% composition, and traces of other elements like aluminium, calcium, silicon, carbon, sulfur, etc. Okay, what are the uses of these metals? Usually, alloys are made to increase the durability, strength, the tensile strength. Okay, so what are the uses of this particular alloy? So it is used in tracer bullets and shells. In bullet making, it is used bullets and shells, and used in cigarettes and lighters. Used in cigarettes and lighters, gas lighters. It is also used in flame throwing tanks. Question number 28. What are inner transition elements? Decide which of the following atomic numbers are the atomic numbers of the inner transition elements: 29, 59, 74, 95, 102 and 104. So they have asked us to identify whichever element is an inner transition element. Okay, they have given the atomic number. First, what are inner transition metals? Let's see. Inner transition metals. The metals or the elements, in which the last electron enters the f orbital. These are inner transition metals. And the elements and the elements in which 4f and 5f orbitals, 4f and 5f orbitals are progressively filled are called F block elements. So amongst the elements whose atomic number is given, so the elements which belong to inner transition series of metals are with atomic number, I'll write AN with atomic number. It is 59. You can check it out actually. You can see the electronic configuration. 59, 95 and 102. 59, 95 and 102. These 59, 95 and 102. These are the elements which belong to inner transition elements. Question number 29. The chemistry of the actinoid elements is not as smooth as that of lanthanoids. Justify this statement by giving some examples from the oxidation state of these elements. So actinoids, the difference between actinoids and the lanthanoids. So let's start. Lanthanoids usually project 3 oxidation states. Which are those? +2, +3 and +4. Out of which +3 is the most common oxidation state. Okay, out of which +3 state is the most common. Lanthanoids display a limited number of oxidation states. Why? Because the difference in the energy between 4f 5d and 6x orbitals are quite large. So they cannot exhibit n number of oxidation states. On the other hand, actinoids display a large number of oxidation states. They display a large number of oxidation states. Why? Because the energy difference amongst their orbitals, the energy difference between 5f, 6d and 7s orbitals are very less. Let's take some examples, because I have asked us to give some examples. Okay, example uranium, and plutonium. Uranium and plutonium display +3, +4, +5 and +6 oxidation states. Neptunium displays +3, +4, +7, +5 and +7 oxidation states. Okay, even when it comes to actinoids, the most common oxidation state is +3 again. Okay, so the chemistry of the actinoid elements is not as so smooth as that of the lanthanoids. Question number 30 is very simple. Which is the last element in the series of the actinides? Write the electronic configuration of this element. Comment on the possible oxidation state of this element. So which is the last element? That is lawrencium. Okay. The last element in actinide series, actinoid or actinide series is lawrencium. What is the symbol? It is Lr. Okay. So it is the atomic number. The atomic number of lawrencium is 103. So the electronic configuration, I'll write EC. This is electronic configuration is radon, which is a noble gas, nearest noble gas, followed by 5F14, 6D1 and 7S2. And the most common oxidation state, displayed by this element, lawrencium, is +3. Why? Because if it loses 3 electrons, it attains a stable 5F14 configuration. You necessarily need not write 5, but yes, this is fully filled configuration. Okay, F14. So it is completely filled. So it is very stable. Okay, so the most common oxidation state, most stable oxidation state is +3 in case of lawrencium. Question number 31. Use Hund's rule to derive the electronic configuration of cerium 3 plus ion and calculate its magnetic moment. We know the formula for magnetic moment. We have to calculate the value on the basis of spin only formula. So first we need to write the electronic configuration of cerium. So what is the electronic configuration here? Cerium 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 4f1, 5d1, 6s2. As it is in its 3 plus oxidation state, we need to remove 3 electrons. Okay. So if we remove these 3 electrons, what will be left? Cerium 3 plus 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 4f1. So the magnetic moment can be calculated using the formula nu is equal to root of n of n plus 2. What is n? N is the number of unpaired electrons. Okay. So in case of cerium, number of unpaired electrons is equal to 1. See here, evidently, here it is 1. Okay, because we have removed 3 electrons. Okay, and this is half filled. Okay, yes. This is not half filled. Sorry, it is completely filled. P orbital. 5p orbital is completely filled. All of them are paired up. So the unpaired electron is only 1. We'll substitute n by 1. So yes, nu is equal to magnetic moment. So root of 1 plus 2. Okay. So it is going to be 3. Root of 3 is nothing but 1.732 bm. Okay. Yes. So this is the magnetic moment value. Very simple. 32nd question. Name the members of the lanthanoid series which exhibit +4 oxidation state and those which exhibit +2 oxidation state. Try to correlate this type of behavior with the electronic configuration of these elements. So which are those? Let's make a column so that we distinguish it entirely. So whichever shows +2 oxidation state and +4 oxidation state. So neodymium, it shows +2 as well as +4 oxidation state actually, NB. Then we have samarium, SM it is. Next we have EU, europium, EU, thulium, tium, YB, ytterbium, YB. These are few of the elements which show +2 oxidation state. On the other hand, +4 oxidation state, cerium, Ce, cerium, PR. What is PR? It is praseodymium. It is praseodymium. Next, again, Nd, that is neodymium. And then we have Tb, that is terbium, and Dy. So it is Dy, I'll write here, dysprosium. It is dysprosium. So this is about the elements which show +2 and +4 oxidation states respectively. So when it comes to Tb, I'm not going to take the names again. So Tb, after forming +4 oxidation state, attains the stable electronic configuration of xenon followed by 4f7, which means that it is half filled. Okay, ytterbium, YB, after attaining its +2 oxidation state, YB 2 plus or +2, attains stable electronic configuration, I'll write EC, electronic configuration of xenon followed by 4f14, which is completely filled. Okay, next europium, EU, after forming EU2 plus, it exists in its 2 plus oxidation state, right? So attains the stable electronic configuration of xenon 4f7, again half filled. Next we have cerium, after becoming cerium 4 plus, attains the electronic configuration of xenon. So noble gas configuration is very, very, very stable. So this is the comparison. Question number 33. Compare the chemistry of the actinoids with that of lanthanoids with reference to electronic configuration. Subquestion 2, oxidation state, and third point, chemical reactivity. We have to compare these two with respect to these characteristics. So let's start. The electronic configuration. We know the general electronic configuration of actinoids as well as lanthanoids. I have to just write down that. So lanthanoids have general electronic configuration, xenon followed by 4f1 to 14, 5d 0 to 1, 0 to 10, 6s2. Okay. Next, actinoids have general electronic configuration. It is radon followed by 5f1 to 14, 6d 0 to 10, and 7s2. So we have compared the first point, the electronic configuration. Next one is to compare them with respect to their oxidation states. So when it comes to oxidation states, the +3 oxidation state is the most commonly shown oxidation state. But apart from +3 oxidation state, lanthanoids show plus 2 and plus 4 oxidation states. Plus 4 oxidation states. What is the reason? We have already studied that in the previous question, couple of questions before. So why? Due to the large gap between phi F and phi D subshells. Okay. So what large gap? The large energy gap. Energy difference is very much between 4F and 5D subshells. Okay. And actinoids show large number of oxidation state. They show large number of oxidation states due to small energy gap between 4F and 5D. Sorry, it is 5F and 60. Okay, 4F and 5D in the lanthanoids. In actinoids, it is 5F and 60 subshells. Next, the third point, we have to compare lanthanoids and actinoids with respect to chemical reactivity. Highly electropositive lanthanoids usually have similar chemical reactivity. They have similar chemical reactivity. On the other hand, actinoids, electropositive and highly reactive, actinoids are more reactive. These are more reactive, okay, than lanthanoids. So actinoids, which are electropositive and highly reactive, these are more reactive. They show more reactivity than the lanthanoids. Question number 34. Write the electronic configurations of the elements with atomic number 61, 91, 101 and 109. So we need to write the electronic configuration of the respective elements. Let me change the color first. Yeah. So with 69, so which is that element? It is promethium. What is the symbol? It is PM, not Prime Minister, but it is promethium. Okay. So atomic number is 61. Atomic number of promethium is 61. What will be the electronic configuration? Let's write xenon. So 54 is the atomic number of xenon, followed by 4F5, 5D0, 6S2. This is the electronic configuration of promethium. Next element is protactinium. Okay, that is Pa. It is the element with atomic number 91. Atomic number is 91. Electronic configuration is going to be radon, whose atomic number is 86, followed by 5F2, 6D1 and 7S2. Next one with atomic number 101. So which is that element? It is mendelevium. So it was named after the scientist Mendeleev. Gregor Mendel, not Gregor Mendel, but Mendeleev. Okay, so who proposed the periodic classification? Yes, MD is the symbol. Electronic configuration is going to be radon, followed by 4F13, 6D0, 7S2. This is the electronic configuration. We are left with the last one with atomic number 109. Atomic number 109. Wherever I have written AN, it is atomic number. Okay. So which is the element? It is meitnerium. What is the symbol? MT. What is going to be the electronic configuration? Radon followed by 5F14 6D7 7S2. 7S2. This is the electronic configuration. Question number 35. Compare the general characteristics of the first series of the transition metals with those of the second and the third series metals in the respective vertical columns. And we need to give special emphasis on the following points. We have to compare the properties with respect to electronic configuration, their oxidation states, ionization enthalpies, and atomic sizes. So let's start with electronic configuration. Okay. So when it comes to electronic configuration, we need to compare the respective ones, the first transition, the second and third. So in the first, second, and third transition series, the 3D, 4D, and 5D orbitals respectively are filled. Okay, and the elements in the same vertical column generally have similar electronic configuration. Let's take some examples. So in the first transition series, two elements show exceptional or unusual electronic configuration. Which are those? Copper and chromium. Copper's electronic configuration, its atomic number is 29. So 3D 10 4s 1. So this will be the nearest noble gas configuration followed by 3D 10 and 4s 1. Chromium 24. So 3D 5 4s 1. Why is it not 2? Because 3D 10 is the completely filled orbital. That's why not at instability. 3D 5 half filled. So these are exceptions. Similarly, there are exceptions in second transition series as well. Okay. Example, rhodium 45, 4D8, 5S1, and molybdenum, so 42, 4D5, 5S1. Okay, these are exceptions. There are more exceptions, but let's take the example of just 2. Okay, and in third transition series, exceptions in third transition series. So which are the exceptions here? These are some exceptions here also. It only depends upon the stability. Okay, platinum. 5D9, 6S1, tungsten, 5D4, 6S2. Okay, so these are some exceptions. Now let's compare the oxidation state. Okay, let's compare the elements with respect to their oxidation state. So this is the second point that we are taking, oxidation states. So what happens? In each 3 of the transition series, the number of oxidation states shown by the elements is maximum in the middle, middle, and minimum at the extreme ends. At the extreme ends. But +2 and +3 oxidation states, +2 and +3 oxidation states are quite stable for all the elements, present in the first transition series. And all the metals present in the first transition series, they tend to form stable compounds in their +2 and +3 oxidation states. The stability of +2 and +3 oxidation states decreases. The stability is going to decrease in the second and third transition series. The stability of +2 and +3 oxidation state is high with respect to the first transition series. But when it comes to second and third transition series, the stability of +2 and +3 oxidation state is going to decrease. Okay. But higher oxidation states are more stable. Oxidation states are more stable. Okay. Next, we have to discuss with respect to what points? With respect to ionization enthalpies. It is ionization enthalpies. With respect to ionization enthalpies. So, in each of the three transition series, the first ionization enthalpy increases from left to right. But there are exceptions. There are always exceptions in chemistry. But there are exceptions. The first ionization enthalpies, I'll write IE, that is ionization enthalpy of third transition series are higher than those of the first and second series. Okay. Why this occurs? This occurs due to the poor shielding effect of 4f electrons in the transition series. And this occurs and also because of the poor shielding effect of the 4f electrons in the transition series. Okay. And few elements in second series have higher first ionization enthalpies than elements corresponding to the same to the same vertical column. Same vertical column. Same vertical column in the first transition series. In the first transition series. Transition series. And there are few elements in the second transition series. There are elements in the second series, transition series, whose first ionization enthalpy, whose first ionization enthalpies are lower than those elements corresponding to the same vertical column, same vertical column in the first transition series. In the first transition series. Now final. So we have to compare with respect to the atomic size. Okay, when it comes to atomic sizes. So what is the comparison between the first, second and the third transition series? Let's see. We'll write atomic size. So atomic size generally decreases from left to right across a period. This is the general trend. Okay, right across a period. But among the three transition series, the atomic sizes of the elements belonging to second transition series are greater than those of the elements corresponding to the same vertical column, in the first transition series. Okay, but let me erase this. So, however, atomic sizes of the elements, in the third transition series, are virtually same as those of the corresponding members in the second transition series. Why? Because this is due to lanthanoid contraction. Lanthanoid contraction, actinoid contraction is very, very important. These two concepts. Question number 36. Write down the number of 3D electrons in each of the following ions. There are few ions that are given here. Titanium 2+, vanadium 2+, chromium 3+, manganese 2+, iron 2+, iron 3+, cobalt 2+, nickel 2+, and Cu 2+. Okay, copper. So indicate how would you expect the 5 3D orbitals. Which are the 5 3D orbitals? So we have T2G and EG set of orbitals. So how are we going to accommodate the electrons in those respective orbitals, respective energy levels? We need to indicate that. Okay, so we'll write the metal ion here, metal ion whichever is given, and we'll write the number of d electrons in each of those, number of d electrons, and we'll show the filling of d orbital in two separate set. Okay, T2G and EG. So metal ion given, Cu2 plus is given, and we have nickel 2 plus, and we have CO cobalt 2 plus, Fe 3 plus, Fe 2 plus, and we have Mn 2 plus. Okay, we'll continue in the next page. So in copper 2 plus, number of d electrons are 9. In case of nickel 2 plus, it is 8, and 7, 5, Fe 2 plus, it has 6 and 5. Okay, how are we going to accommodate the respective electrons in T2G and EG? We'll write it in here, T2G 6, and in EG we have 3, and in T2G we have 6, and in EG we have 2 in case of nickel 2 plus, and in cobalt it is T2G 5 and EG 2. In Fe3 plus it is T2G it is 3, and in EG we have 2, and Fe2 plus T2G4 EG2, and manganese 2 plus, it's going to be T2G 3 EG 2, EG2. Let's move on to the next page. So the same thing here, metal ion, the number of electrons in the d orbital and the filling of d orbitals. Okay, we are left with chromium 3 plus, and we have vanadium 2 plus, and then we have titanium 2 plus. So how many number of electrons are there? In chromium it is 3 in d orbital, and 3 in vanadium 2 plus, and titanium has 2 electrons in d orbital. So in case of chromium 3 plus, it is going to be T2G3. Okay, even in vanadium it is T2G3. Titanium it is T2G2. There is no EG, so there is no electron in EG. Okay. Yes, this is about the metal ions and their respective number of d electrons and filling up of d orbitals. Question number 37. Comment on the statement that elements of the first transition series possess many properties different from those of heavier transition elements. So how can we give some pointers? First one. So the elements in the first transition series, in the first transition series form low spin or high spin complexes, of course depending upon the strength of the approaching ligand, that is approaching. Okay, the heavier transition metals, the heavier transition elements can usually form only low spin complexes, okay, irrespective of the strength of the ligand. One difference, strength of the ligand. So this is the very first difference. What can we write? So the melting point and the boiling point. The melting and boiling point of first transition series elements are lower than those of the corresponding those of the heavier transition elements. Heavier transition elements. Why? Because of occurrence of stronger metallic bonding. Stronger metallic bonding. Okay, the discrepancy in the melting as well as boiling point. And the enthalpies of atomization. The enthalpies of atomization of the elements in the first transition series. In the first transition series are lower than those of the corresponding series in the corresponding elements in second and third series. Second and third transition series. We are done with the third point. Next, anything that you can recall. So, if we talk about the oxidation state, the higher oxidation states are quite common for heavier elements. But for first transition series, which oxidation states are common? +2 and +3 oxidation states are common. Okay, so this is about the differences between the first transition series and to those of the heavier transition elements, that is second and third transition series. Last question, question number 38. What can be inferred from the magnetic moment values of the following complex species? So 3 complexes are given. We need to deduce. We need to give explanation for the following. Okay. So they have given the magnetic moment. Let's see. We already know the formula for calculating the magnetic moment. It is root of n plus 2. And it will be calculated in Bohr magneton. This is the unit. Okay. And n is the number of unpaired electrons. If the value of n is equal to 1, the magnetic moment is going to be approximately, so it's going to be root of 1 plus 2. So root of 3, which is equal to 1.732 Bohr magneton. Okay, if n is equal to 2, magnetic moments, the same type we have to calculate. It is going to be 2.83 Bohr magneton. If n is equal to 3, the magnetic moment is going to be approximately 3.87 Bohr magneton. If n is equal to 4, the magnetic moment is going to be 4.899 Bohr magneton. If n is equal to 5, the magnetic moment is going to be 5.92 Bohr magneton. So we already know till the value n is equal to 5. So if we see the complexes here, so this is the first complex that they have given. So here cyanide is a ligand. We know that cyanide is a strong field ligand, but let's infer. Okay, let's give explanation to this. So root of n plus 2 is equal to 2.2 Bohr magneton. So they have already mentioned here it is 2.2 Bohr magneton. Okay, so yeah, n of n plus 2 is 2.2 Bohr magneton. So which is approximately equal to which value here? Which value? So for transition series, transition metals, the magnetic moment is calculated from the spin only formula. Okay. So if we see the value that they have given, okay, the closest is n is equal to 1. And in this complex, if you calculate the oxidation state, manganese is in +2 oxidation state. +2 oxidation state. You need to remember the how to calculate the oxidation state and which are strong field ligands and which are the which are not strong field ligands. Okay, and we need to remember the electronic configuration of the respective ions. Okay, as Mn is in +2 oxidation state, how many electrons are there in the d orbital? It is 5. Okay, so in this complex, Mn is in +2 oxidation state, which means that this means that there are 5 electrons in d orbital of the metal, that is manganese. Okay, hence we can say that Cn minus is a strong field ligand because it caused pairing up. That's why the magnetic moment value is less. Okay, strong field ligand which causes pairing of electrons. See here, d. Okay, this is d orbital. So there were 5 electrons in Mn2 plus. As there is a strong field ligand that is approaching, pairing up happened and this went here. Okay, yeah, so pairing up occurs. That's why the closest value is n is equal to 1. That's why the magnetic moment is lesser. In the next complex, we have aqua, water as the ligand. Is it a strong field ligand? No, it is a weak field ligand. Okay, we already know this, but we need to give explanation with respect to the magnetic moment. Okay, we have 6 weak field ligands, that is water. Okay, and the complex is in +2 oxidation state, and the magnetic moment is already given in +2 is equal to 5.3 Bohr magneton. Thus, the calculation given above proves that what could be the nearest or closest value of n in this if it is 5.3. Let's go back. Let's see. So where is it? So this could be the nearest, closest value, right? Yeah. So n must be 4. Okay, n is equal to 4. Calculation given above proves that the closest value to n, the closest value of n is equal to 4. Okay, and the complex is in +2 oxidation state. So, of course, metal Fe is in +2 oxidation state because this ligand doesn't have any, it has 0 charge, this ligand. Okay, +2 oxidation state. So the d orbital of the metal ion, the d orbital of metal, that is Fe, would have 6 electrons. Because +2 oxidation. Okay, Fe2 plus will have 6 electrons. So how is that possible? See here. 1, 2, 3, 4, 5, 6. But H2O is a weak field ligand, right? Weak field ligand. And by the value of the magnetic moment, so we have deduced that the closest value of n is 4. Okay. So thus we can assume that or deduce that H2O is a weak field ligand. It's a weak field ligand, and does not cause pairing up, does not cause electron pairing. It's not done. We have another complex. So which is the another complex? K2MnCl4. Here chloride ions. This is the ligand. Okay. And the magnetic moment value is given here, which is approximately equal to 5. Not approximately, but they have given the value 5.9 Bohr magneton. Okay. Let's go back where we had calculated. So it is this value. So N is equal to 5. The same way we need to write. Okay. So the closest value of N is equal to 5, or nearest value. And manganese, so which is the central metal atom, is in +2 oxidation state in this complex. +2 oxidation state in this complex. See here, this has 2 plus, so it's going to be -2. Okay. So yes, +2 oxidation state. Okay. Which means that the d orbital will have, d orbital of Mn has 5 electrons. It has 5 electrons. Okay. So we can assume, that Cl minus is a weak field ligand, and does not induce electron pairing. That's why the magnetic moment is more here, which is equal to 5.9 Bohr magneton. Okay. So this is very simple. So even though you know if it is a strong field ligand or weak field ligand, you have to give the justification with respect to the magnetic moment they have given. Thank you so much. So this is all about this chapter, the NCERT questions. So read it thoroughly, study this thoroughly. Okay. If you have any doubts, you can mention in the comment section. Thank you so much, and please do subscribe to the channel.